we want to calculate the heat capacity of this example, but via quasi-potential. Okay? The example is, do you remember this two-level system with the switch? Now imagine one dynamic over X is diffusion type dynamic, and for the Y is just flipping between minus and plus between two states. And the potential is as follows. It does have both Y and X. C is coupling Y and X with this potential. The main question is here is that, okay, I want to build up, to establish my Poisson equation to find quasi-potential. So to find Poisson equation, I need to find what is the heat. And then after finding the heat, solving Poisson equation, I do have the heat, quasi-potential, and I can find heat capacity. For any given system, for any Langevin type dynamic, do you realize this kind of dynamic? Can you realize it? This is just diffusion type dynamic that we have. And okay, to find the heat itself, we look at the first law. And to find this U is exactly the same U. Here, just go through, I'm giving you part of, the idea of the proof to find the heat. I start to find these kind of things, to find du, and with Taylor expansion, E to approximation. Have you ever heard about these kind of things? If not, it doesn't important. Just know that we start from the first law, okay? And then the heat power, xy is it's related to the energy in the first law, and this one is related to the work. This is the heat power that is coming from here to find the heat, means coming from energy and the work. And what is L? Okay, sorry, I should have think about it to organize my board. Just consider these things. L, somebody asked me this generator, L here, for any given V, is applying as like that. Okay, we know how generator L is applying on the function, and we know from the first law what is heat. It's very important to realize what is heat for any given system. But look from where I'm starting. From the first law I'm starting. There is nothing strange. Just from the first law I'm starting to find the heat. Okay, that is from the energy and work and it's affecting, and I do have my P, and I put P, and I take the average to find a stationary P, and put it here. I have right-hand side, I have left-hand side, and okay, just find V. Just find it. Okay? And then the heat capacity of such a system via quasi-potential is obtained, and you can see that it's not a function of the temperature as it is a constant. It's not always like that, just in this system, it's interesting. This is via quasi-potential. Calculating the heat capacity via quasi-potential, it's very theoretical. Yes?
Sorry, so A is an operator, right?
Yes, yes.
And B is the quasi-potential.
Yes, yes.
And the idea is to find the quasi-potential in this case.
Yes.
Right? And the operator L, so what is the operator L here? So
it's just, for any, maybe it was better I gave you any function. I want to just tell that how it's applied. Yes, yes. Yes, yes. Yeah. Sorry. Yeah, it's and it depends. In any system, it depends on what is your operator. I want to just emphasize that this Poisson equation, if you are in discrete space, it works. If you are in a diffusion continuous space, it works again. It's okay. And okay, in theoretical setup, it's painful to find a quasi-potential, but it's possible, and it has nice information inside. And yes.
Quick question. So do you really need the, okay, I think I asked this many times, but you have the Ito equation for heat, no?
Yes.
Isn't that enough to calculate the heat capacity?
You mean just from the Q here?
From the P. You have P there.
You mean here?
Yes.
Then what is heat capacity?
I'm asking, isn't there a way to calculate heat capacity from that formula? From the specific heat equation? With some mathematical manipulation?
No, because if I want to answer that, I repeat, I'm in the cycle, in the sense that I do have this heat power, then I want to put it for the Poisson equation, because the definition, because I'm interested to the excess heat. Yeah, I'm again in the cycle.
But if I have an Ito equation for the excess heat, so this is Ito for heat total. But there is an Ito equation also for the excess heat.
Separately?
Yes.
That I don't know. Maybe it's the things that you already explained me.
Probably.
Yeah. Yeah. Perhaps it's this one, but I don't know. Sorry. Yeah. Okay. Now there is another way exactly for this question. For this kind of example, this question via AC calorimetry. Do you remember I asked you what is the definition of heat capacity? You told me that, okay, we are changing the temperature, we are giving the heat to the system, and then we are looking at how much temperature is changing. Or we are changing the temperature, we want to see that how much heat is exchanging with the environment. But nobody told that how you are changing the temperature. Linearly, with a function. Okay? This is the method. That here, in AC calorimetry, people change the temperature with a sinusoidal wave function, and then they look at the response of the system. But it doesn't mean that because temperature is changing strangely, then definitely you are non-equilibrium system. No, temperature is just a method, even for the equilibrium system. They just change the temperature of the heat in a strange way. Why? Because they work with Fourier transform or this kind of thing. But what is the setup for the AC calorimetry? They put the sample, they contact the sample to the heat, and how they want to make sure that the sample can receive the heat or transfer the heat to the sample perfectly. They measure it with the thermopile in the sense that they're changing the electricity to heat and these kind of things. But the point is that we want to measure that for non-equilibrium system in the sense that the sample, it should be in non-equilibrium. How we do work on the sample. Okay? And the AC calorimetry, I mean, this is a paper by Kirsten and Carl in 2019, that the temperature is changing, it's time dependent, and there is a delta T and omega frequency to change the temperature, but they are very, very small. You're perturbing the temperature very small. And then you look at the heat power, and then you plug it in this equation. The heat capacity is here. Okay? If I, for example, for the flashing potential, I just plot the heat power, and because the temperature is changing during the time with a sinusoidal wave, the heat power also, after it get to the steady state very fast. You see, it doesn't behave very nicely. And then we just look at do you remember the formula? We just look at the cosine coefficient for the Fourier expansion. Okay? And this is just the heat capacity that you can obtain. But to show that, oh, this AC calorimetry can work in any system, just for two-level system that is in equilibrium, I did the same. This is just the one possible trajectory for the particle in two-level system that is in equilibrium. It's just jumping between a state 0 and 1, I don't know, yes, 0 and 1. It's just very random. This is a simulation. And I did the simulation for many, many particles to make sure to take the average. And then I plot the heat of the system, and then I fit it with the formula that I had. And the cosine coefficient is the heat capacity. And I did it. Look, the heat capacity with this approach, and I'm very impatient for simulation. Imagine I was just waiting up to result come. I cannot leave the program to do it for a long time. I did it for a very small average. I mean, it's not that much precise, but look, it's very precisely same as the theoretical heat capacity. If you do it with patience and I mean, a small delta T and a small omega, and take average a lot, then your answer is even more precisely. Okay? And recently, Christian is collaborating with the experimental, Christian, my supervisor, is collaborating with the experimental group. Now I'm going to the lab as well. We are interested to measure now the heat capacity, non-equilibrium heat capacity. Nobody has done it before. And the experimental setup is that we have our sample. The sample is that one. I mean, I myself surprised with the size. We have our sample. And the sample is ferroelectric material. Do you know what is ferroelectric? Ferromagnetic ferroelectric, you know, I mean, just science. I mean, it has some dipole, and it's sensitive about the electric field. And when electric field apply on that, the polarization is happening. Why we choose this strange material? Because we want to make it non-equilibrium. And if we apply electric field on that, polarization current also is happening. So, oh, okay, the material that we use is a crystal, and it's TGS. It's called TGS. It's a very it's an abbreviation of a very strange chemical name. I forgot it. Sorry, but it's called TGS. But it's not an R abbreviation in the sense that if you search TGS, you can understand what is that. It's a crystal. And okay, this experimental group, they like this material because they really like to look at the polarization current and this kind of thing. But and also heat capacity. But they never have done non-equilibrium heat capacity. I mean, whenever electric field applied on the crystal, now we want to measure the heat capacity. This one is very new. I mean, they did it before when there is no electric field. They can measure the heat capacity, or they applied electric field to measure the polarization current, but they didn't do that together. I mean, to have a non-equilibrium system. And okay, this is for the equilibrium case. And this is just the data that I collected from the lab in the sense that we change the temperature with AC calorimetry. We have a bath. We put our crystal into calorimeter. That is with, I mean, it's something completely isolated and with the Peltier element that is the shield is contact to the sample. Then make sure that sample can receive the heat and exchange the heat with the environment correctly. And they look at, I mean, the Peltier element is changing the heat to the voltage, and you can see what's happening for the system. And we change the temperature slowly. You see it has a ramp as well. But the ramp slope is very, very small. I mean, imagine every round of the experiment is going for 1 week. The temperatures start from 20 to 70 degrees Celsius in 1 week. So this is very, very small slope. And then we look at the heat capacity. This is the heat capacity that we plotted. I mean, I plotted the heat capacity. And then you see in 57 degree, the temperature when it's 57, a phase transition is happening for, I mean, it's a critical point for TGS. So the heat capacity, the peak is going on and coming down. But this is in equilibrium. For non-equilibrium, we tried several times, but still we are not in non-equilibrium system because our electric field wasn't that much strong. We were in a close to equilibrium, not far from equilibrium. This is an experiment that is going on. And okay, this is just via AC calorimetry. You saw that in simulation it works. And in an experimental setup also, we like to measure the heat capacity, non-equilibrium heat capacity. Let's not tell non-equilibrium heat capacity, say heat capacity of non-equilibrium system. This is better because I remember when I taught, one student asked me, okay, what is the equilibrium heat capacity of this system? And it isn't like that. We are not separating that. It's the heat capacity of a non-equilibrium system, okay? And now, after all of the story, you understood what is the calculation, what is the measure, how we can measure that. And now I want to show you some very interesting features that it has. Okay, look, some question, for example, what is the heat capacity in a close to equilibrium regime when you are not far from equilibrium, in a linear order of non-equilibrium? And what is the meaning of negative, I mean, it's negative heat capacity appeared, you see in the calculation, and what's going on for the negative heat capacity? I mean, what's the meaning of that? Another thing is that what is the heat capacity at low temperature? The rest of the talk, I want to cover these 3 points. Close to equilibrium heat capacity. In the close to equilibrium, my meaning is that the term that is non-equilibrium in your system is linear. I mean, if you expand it, whatever you have, this distribution that you have, If you expand it, you are in a linear order of that, okay? And there is a distribution, famous distribution here, that is Maclaurin distribution, that it's in terms of the equilibrium distribution plus one correction. But the interesting point is that this correction is a kind of Poisson equation. It's a kind of quasi-potential of this term that we do have it here. And forget the rest of the things. Just look at the formula. This is itself one paper. Just look at the formula. You see, it's nothing strange on that. We don't have quasi-potential. We don't have excess heat. It's just in terms of the energy. And it's very handy. It's very nice formula for closed equilibrium heat capacity. It's just in terms of the energy. And what is this average? Average is over the Maclaurin distribution. Okay, close to equilibrium distribution. This is very nice formula that we do have it for the close to equilibrium, and it's properly working. The other point that I want to tell is related to negative heat capacity. In some example, we saw that it's possible that heat capacity can be negative, but what's going on really there? Do you remember I gave you this formula for the heat capacity? If I just open that, because the average of quasi-potential is 0, I can write it as follows. And then I can write the heat capacity, just very simple, just very simple. There is no proof in between, okay? As a covariance between V and log rho. Log rho is giving me the feeling of Boltzmann entropy. It gives information related to population. And V gives us some related to Clausius entropy, related to heat. Do you remember it was the answer of Poisson equation when source was heat? So just simply look at this covariance, because in equilibrium, the heat capacity was as follows. It was just this way. And never can happen that the average of the energy can be, the negative or something like that. It can be always positive. But here, it's the covariance. Just mathematically, you know nothing. It shows you that, yes, it's possible you have negative. Of course, here is, it means that it's possible that there are strange behavior happening here. Okay, they both strange behave. It's possible. It gives you just some possibility mathematically. But what's happening here? To define this negative heat capacity, we first define effective temperature. Effective temperature is just a tool to show you population in the system. And then via that, we could establish very strict condition then when heat capacity can be negative. You see, you can understand that, it seems that when population inversion is happening in the system, then heat capacity can be negative. Not always, because the condition, sufficient condition, but it can happen. But look what's happening here. For example, if I have a ladder, and instead of 2-level system, I have 3-level, and the energy landscape, they're switching to each other. A plus, a minus, and plus. And the barrier is just delta, and I have different level of the energy, eta 1, 2, 3. And epsilon, the energy is changing. There is alpha transition between 2 leg and 2 landscape. And there is also another dynamic to change the level of the energy. Okay? In this system, the lowest, here in previous slide, I didn't tell you what is X star. And luckily nobody asked. X star is the lowest quasi-potential. And in this system, the lowest quasi-potential is this state, but it's symmetric with this state. So I have the SSR in my system is this one. It's the lowest quasi-potential, and it's the ground state. I mean, in a normal situation, the particle likes to stay here. Okay? But when I change the temperature, then something, if I change the temperature, from the ground state, the particle likes to go to higher state. And I see that, oh, it's possible in some cases I have negative heat capacity. For example, here. When, I don't know, what is I can see from here better. When epsilon is 1, delta is 1, and then I have a big negative heat capacity. And if I write down the condition in terms of, instead of beta, I write it down in terms of temperature, the condition is as follows. An explanation here is easier. Look, I don't know if you see here or not, but something that is happening. Look, the things that is happening here. In the regime, for example, the temperature is around 0.2. Heat capacity is negative, 0.2. And now around 0.2, my ground state, if it's equilibrium, just the particles go up, the population is decreasing for the ground state. But here I'm in non-equilibrium setup, and the population is increasing. I'm changing the temperature because the rate also is changing, the switching rate. This slope is positive. This slope is positive. And here energy is positive. This is power 2, everything is positive. The negativity of heat capacity can only be from here, the derivative of effective temperature. And the effective temperature here, a slope is very sharp negative. Okay? So in this regime, there is something strange happen. The ground state is behaving strangely, and my heat capacity also get negative. It means that what's going on to the system? You are giving heat to the system, and instead of changing the temperature, the heat is using for the changing the normal population distribution in the system. Okay? So heat capacity can get negative. It's one interesting point here. And to define that, we define effective temperature. That is just a tool to describe about the population distribution, actually. And another point, okay, what is the inertia theorem? Do you know that? You tell me. Somebody tell me, what is the inertia theorem? I told this third law of thermodynamics. Whenever temperature is going to 0, the heat capacity is going to 0. Very nice question that we can ask here is that, okay, Faezeh, thank you. You gave us heat capacity in non-equilibrium. You measure that, you calculate it. And the question is that what happened for the inertia theorem? The heat capacity at low temperature, whether it can go to 0 again as well, or if not, what's happening for the system? This is the work that we have done for my PhD thesis. And you see, in equilibrium system, the heat capacity the third law itself, it's called law, but it has some condition. Because of that, some people believe that, no, it's not a law. Because it has condition. It took, I think, historically 20 years up to people accept it as a law because it had some condition. And of course, the Planck version is telling that the heat capacity at low temperature is going to 0. But on the other hand, there are some crystals that, for example, ice spin, when you are going to zero temperature, you have the entropy is 2, and the entropy is not going to 0. Okay, and it has one condition, that if your ground state is unique, then the entropy is going to 0. If you are just, this law is just valid for the system that the ground state at zero temperature is unique. And here, luckily, just mathematically, we need also to have a ground state, unique ground state. But here in non-equilibrium, we have another condition as well. We have dynamical condition. So we have two conditions, unique dominant state. Another one is that your quasi-potential should be bonded. And I will tell you what is the meaning of that, why it should be bonded. And with these two conditions, then heat capacity at zero temperature goes to 0. Okay? Do you remember we write down the heat capacity as like that? And if I want to take the limit to go to 0, to temperature go to 0, if this one is unique, if this one is bonded, and this one go to 0, then the limit, the answer is 0. Just in very elementary level of a school. If this one is, if V is bonded, and D rho is going to 0, then the whole expression is going to 0. Okay? And now we are looking at what is the meaning of bonded quasi-potential. We understood with solving Poisson equation, we understood that the quasi-potential is related to first passage time. Means that, just imagine, I have a system, I have unique dominant state. It means that at zero temperature, all of the particle wants to come here to meet the unique dominant state. And just imagine there is a high barrier between me as a dominant state and another particle in the corner of the room. The particle should make too much work that is in the same feeling with the quasi-potential up to reach the dominant state, up to reach the unique dominant state. Means that the time that the particle wants to meet me is too much. So we are telling that quasi-potential should be, then in this case, when it's too much, the particle, the heat is localized in a system, the heat capacity is not going to 0. The third law is diverging. The heat capacity is diverging and the third law is not valid. Okay? So I need quasi-potential be bonded. And to do that, we give bond for quasi-potential with the first passage time. We solved Poisson equation. This is Poisson equation for quasi-potential, and this is a kind of Poisson equation for first passage time. This is, do you know what is first passage time? The first time that if the processor starts from X, meet Z. The process is just random. It's stochastic. And they run the process several times and take mean and to see that what is the first time that meet Z. They start from X and just run it and randomly go and just meet and stop. Again, run it and stop. And then they take a mean of that. They have the time. How much time, what is the first time that the process start from X can meet Y? For example, it can Z, I don't know here, what's that? And we give upper bound, because the Poisson equation are related together, we give upper bound to quasi-potential. And we see that, oh yes, if in system, for any given, the processes start from everywhere, if the first passage time is not infinity, and it's finite and it's bounded, then quasi-potential also is bounded. And I gave you the meaning of that why we care about the bounded quasi-potential. And then if quasi-potential is bounded, then the third law is valid. So under two conditions, heat capacity is going to zero. First, having unique dominant state. The second thing is that quasi-potential should be bounded. For any given system, I can see that whether heat capacity is going to zero at zero temperature or not. Conclusion. Okay, we understood that the heat capacity is a thermal response of the given system, and it's looking at the excess heat. And we understood that non-equilibrium heat capacity gives us information related to kinetic, that this is new. And we understood about the third law, that the third law can be satisfied under two conditions. The one condition is exactly same as the equilibrium version, and the second condition is because of the new dynamical condition, new dynamical item that we do have in our system. And it's related to bounded of the quasi-potential, and what is the meaning of that? Means that there is no trap in the system. And dominant state is accessible for all of the state. And by this, thanks. Okay. Yeah.
Thank you very much. It was a very nice talk.
Thank you.
So I was wondering when you can find a quasi-potential. Is it possible that for a system you cannot find a quasi-potential because it comes from a solution, right? From
Yes.
this equation.
Yes. The immediate and naive answer I can tell just mathematically. Poisson equation has answer just in the case that the source is central, in a sense that the average is zero. But okay, but in the practical level, I believe that every time you can, and whenever you can define the heat in your system, then you can find that maybe painful and difficult theoretically, but in theory it should work. And Poisson equation should have an answer for that. But this is a stochastic, what is L here? Whenever is the system, this is, in my knowledge, this Poisson equation just in a stochastic process, whenever L is defined, whenever heat is defined, well defined in the sense that you can realize it. But, okay, thank you.
Thank you again.
Thank you.
But you will be here for...
Yes, I'm around. You can ask your question, a calculation.
If you have other questions, you can approach.
Yes.
Thank you very much.
Thank you.